Day 2 here of the Taylor series. So now we're going to start to use these series to help us with some of our integration. Yeah, pretty much it, because integration is kind of where things get weird. So we cannot integrate this, by the way. We cannot integrate this. It's impossible for us to integrate this in its current form. So what we're going to end up doing here is I'm going to want to rewrite this as a Taylor series. Because that's going to turn this into a polynomial, and I can find the integral of a polynomial. So how do we do that? Well, if e to the x is 1 plus x squared over 2 factorial plus x to the third over 3 factorial, e to the negative x squared is going to turn into 1 minus x squared plus x to the fourth over 2 factorial minus x to the sixth over 3 factorial. You get the idea, right? So what we're going to do here is we're going to go ahead and integrate each one of these. And I don't really know how far to go. So if I need to go further, I guess I shouldn't have ... that one. If I do need to go further, this is going to be x to the eighth over 4 factorial plus, minus x to the 10th over 5 factorial, and you get the idea. Okay, so I'm going to just keep going a little bit here. So if I integrate from 0 to 1 of this e to the negative x squared dx, the same thing as integrating all of these things right here. So x turns into, 1 turns into x. This turns into minus 1/3 x cubed plus 1 over 5 times 2 factorial x to the fifth minus 1 over 7 times 3 factorial x to the 7 plus 1 over 9 times 4 factorial x to the ninth. And I'll just stop right there. If I need to go further, I'll go further. So ... and we're going to be evaluating that from 0 to 1. Okay, so I'm going to do each term individually. So if I do, what's really nice about 0 to 1 is the zeros are just going to all cancel out anyway. So if I do just the x1, I'm going to get 1. Now I'm looking for an error less than 1 over 100. So as soon as I reach a number that's beyond that in the denominator with 1 over 100, then I'll be good to go. So minus 1/3 plus, because again, the 0 is going to knock it out, plus 5 times 2 factorial is going to be 1/10 minus 1 over, that's 42, plus 9 times 4 factorial is going to be 2 something, 216? Yeah, 216. Okay, now here's my error. Remember, error is always from that next term. So I'm going to do a stop and chop. Okay, so now I'm approximating this series with these guys right here. So I'm going to go ahead and take out my handy dandy calculator. I don't need to show you me typing this in. Right? You can get that. I can type this in the calculator. Not a big deal. And you're going to get approximately 0.74285. All right. So this works because we have an alternating series. By alternating series test, all right, the error is less than 1 over 216. And this works again because this is alternating. We can use our alternating test. And we're good to go. So that's our approximation. And again, remember, our error, absolute value of our error, is less than 1 over 216, which is indeed less than 1 over 100. So we're pretty gosh darn close. This is a pretty good approximation of this integral. So yeah, there you go. Now you know how to take the integral of practically everything. All right, so this is going to be kind of sort of Fourier response right here. So find the Maclaurin series for cosine. This is a formula, by the way, that you should have memorized, which is going to be super nice. So you should already have this memorized. So cosine of x is equal to 1 minus, it's even, by the way. Cosine is even, so that's why it uses the even ones. 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial. And here's the general term. It's alternating, so that's why I use that. x to the 2n because it's even all over 2n factorial. Should have been memorized, but there you go. So if this is a free response, it's like a free point right there because you had to memorize it anyway. User answer to find the Maclaurin series for this right here. So what we're going to end up doing here is we're going to do 1 minus this right here and dividing everything by x squared. Okay, so it's 1 minus this entire thing right here. 1 minus this x squared over 2 factorial. It gets a little just repetitive here. Plus whatever. And that's all over x squared. So those ones are going to cancel out, and I'm going to be left with 1 over 2 factorial. Ones cancel out, and dividing everything by x squared. So essentially, I'm knocking all these down by a power of 2. So this is going to become plus, minus alternating, minus x squared over 4 plus x to the 4th over factorial. 6 factorial. And you can kind of get the pattern from there. So it's alternating, so it's going to be x to the 8th over 8 factorial, and get the idea, right? So the general term for this is going to be negative 1 to the n because we are alternating, and it's going to be, and again, if you're just dividing by this, you can use our general term here and be like, oh, we're dividing by x squared. That's going to be just x to the 2n minus 2. Okay, all over 2n factorial. So the only thing that really happened here is changing that to an n plus 1 because I'm now alternating on the evens instead now. So that's all I'm doing right here. Just changing this with the plus 1, changing that with the x to 2n minus 2. So you just might need a little bit of practice with these to get from here to here, but practice makes perfect. Now use your answer to approximate the value of this right here, because again, we cannot take the integral of this. It's very difficult to do. So we have to put this in Maclaurin series so that the error is less than 1 over 1/500. So it's going to be the exact same situation here where we're going to want to find the stop and shop. Okay, I'll be a little bit more formal with this one than I was before because I was just kind of showing you. So since this is error, first off, look at this series right here. It is alternating. It is decreasing in magnitude. And then the limit is 0. I want it right. Yeah, the limit approaches 0. Okay, so when you write this down, now you're enabled to use the alternating series test. So make sure you mention that. I didn't mention that in the first example because I was just kind of like going through teaching you what the process is. But now that we have the process, let's formally do it. Mention that so we can use the alternating series test. So the exact same thing that we just did before is we're going to integrate from 0 to 1 of 1 over 2 factorial minus x squared over 4 factorial plus x to the 4th over 6 factorial. I think this is enough terms. Okay. Should I use t's? I probably should use t's. Luckily, x's can turn into t's kind of easily. So that should be t's. And don't worry, if you don't use t's, AP will say that you just misspelled the letter t. So you'll be fine. Okay, so this is going to be 1 over 2 factorial t minus t the 3rd over 3 times 4 factorial plus t the 5th over 5 times 6 factorial. I'm kind of looking ahead going, yeah, that's probably where I end up stopping because 5 times 6 factorial is a pretty big number here. So I'm going to kind of stop it right there. Evaluate from 0 to 1. Luckily, again, 0. I'm going to cancel everything out. So I'm going to get 1 over 2 factorial, which is 2, minus 1 over 3 times 4 factorial is going to turn into 72, plus this is going to turn into 1 over, holy cow, big number here, 5 times 720, whatever the heck that is. But I don't even need to worry about it because this is clearly beyond that. So I'm going to do my stop and chop. So all I'm going to do here is just do 1/2 minus 1 over 72, which I'll do my handy dandy calculator, which is going to be 35 over 72. And that's my approximation, which is pretty gosh darn accurate because it's off by just 1 over 1/500. And again, the error here, if I can spell error correct, you don't need to actually write down what this real number is. It doesn't matter because we do know that it is indeed less than 1 over 1/500. Okay? And this is by the alternating series test remainder theorem. There you go. That is day 2 for Taylor series.